Yes, the final exam is comprehensive. Okay, the next thing on your schedule is the draft submission for Part 2. Remember, our research paper has 2 segments. It's got the background information, which you've already submitted, and then in Part 2, you're focusing on what are the research aspects of your subject. So you're supposed to be doing the journal research and finding articles that then, you don't just summarize the articles. That's not what you need to do. What you need to do is read the articles and then find a common theme. Try and figure out from the references you've found, what direction does the research seem to be headed in. And so you can certainly mention the sources that you found, but you're supposed to go one step beyond just summarizing what you read and actually synthesize your own analysis. So I'll look forward to reading those. They're due by 5 o'clock on Tuesday. The full assignment description, maybe I'll refer you to that. It's not necessarily a critique because critiques are opinion and maybe making a value judgment. So I wouldn't say critique, I'd say analysis. Yeah. All right. We're talking about air pollution now. And let's start with calculation just to illustrate how concentrations in gases are a bit different from concentrations of things in water. You may remember back in chemistry the ideal gas law. Remember PV equals nRT? So in the ideal gas law, one of the things when you're doing calculations like that you may remember is that the volume of an ideal gas at standard temperature and pressure, a mole of gas occupies 22.414 liters. And so this is the equation we can use to convert between the parts per million and micrograms per cubic meter. Micrograms per cubic meter is a measure of concentration that's used a lot of times when we're talking about air pollution. So just as some example calculations, what if we had a 2.5 cubic meter sample of air? That could be the volume of a small room, for example. And we know that it has a certain mass of H2S. H2S is hydrogen sulfide, and this is a common concern in environmental engineering. It can be formed in wastewater treatment. This gas can sometimes be in sewer pipes when the water's not moving too quickly and anaerobic conditions form. Not only is this gas corrosive, but it's also toxic to humans. And we're not very good at smelling it. It actually deadens your smelling nerves. And so you smell it initially for just a few seconds, but then the smell goes away and you think, oh, the gas must have left. But really what it did is it paralyzed your nose, and then it can cause eventually death if the concentrations are too high. So what is the H2S concentrations in terms of ppm for this one? I'm just going to substitute into the equation. First of all, we have to do our temperature calculations in terms of Kelvin. You'll notice in the formula here it says to use the temperature of the gas in Kelvin. Do you have a question? Anyone? You sure? Okay. Temperature is 273, which is the conversion between Celsius and Kelvin, plus the given 34 degrees Celsius. So that gives us 307 Kelvin. The pressure that we need, here it says atmospheric pressure is 0.98 atmosphere. To get parts per million, we need it in terms of kPa. And so the pressure is 0.98 atmosphere. And the conversion factor between kPa and atmospheres is 101.325 kPa per atmosphere. So the atmospheric pressure of this sample is 99.2985 kPa. The last thing that we need to know is the molecular weight, the gram molecular weight. So how many grams per mole are there of hydrogen sulfide? So the G molecular weight is going to be 2 hydrogens, 1.008 grams per mole for hydrogen, and then sulfur, which is 32.07 grams per mole. So the sum of those is 34.086 grams per mole. Okay, so now let's find out how many ppm we've got. ppm is going to be equal to the mass, and the mass should be in terms of micrograms. If we're given 1.25 grams, the way we convert between the two is 1.25, right, times 10 to the 6th micrograms. So that's the mass. And we have to divide by the molecular weight, which is 34.086 grams per mole, multiply by the volume factor of 22.414. And now the ratio of our given temperature to 273, which is the temperature in Kelvin of 0 degrees Celsius air. So 307 Kelvin divided by 273 Kelvin. The ratio of the pressures, standard pressure is 101.325 kPa. The pressure of our sample is 99.2985 kPa. And now the volume of our air sample is 2.5 cubic meters, and we multiply by 1,000 as a conversion. So if we do all of that, it works out to 377.28 ppm. So this calculation will be included on the homework assignment that I give you next time we meet. This formula is found in the book, and it basically just helps us to account for the fact that in water, it was easy to do our concentration calculations because water is incompressible. The density of water changes a little bit as a function of temperature. It doesn't change at all as a function of pressure, but gases are a lot more prone to changes in temperature and pressure. And so when we're calculating concentration of something, you want to know mass per volume. That's what concentration means, is mass per volume. So the complicating factor with gases is the volume changes, the volume of air changes as a function of temperature and pressure of the air. So that's what this formula allows us to take into account, is how the temperature and pressure of the air volume affects our concentration. The atmosphere has a temperature profile that on average is described by this figure that's shown on the screen. If you've ever flown in an airplane, you know it's really cold in the higher atmosphere. Sometimes airplanes on long transoceanic flights will have like a temperature gauge, and it tells you how cold it is outside. Usually when we're flying at really high altitudes, the temperatures are quite low because it's so cold. Where we are, we live very close to the Earth's surface. We're in the troposphere. You know, the troposphere extends up to around 17 kilometers of altitude. And there's a linearization here. This is a curve, but approximately linear. And what you can see is as you go up in elevation, the average temperature of the air is decreasing. And that's really important for air quality. The higher you go in the atmosphere, the reason for the cooler temperatures, it's interrelated between there's less air at higher temperatures, and that means that the volume occupied by a certain mass of air is much greater. Now, the slope of that line is approximately 1 degree Celsius for every 100 meters of elevation. So how tall is the Burj Khalifa? 800 meters. What this means, this lapse rate, means that at the bottom of the Burj Khalifa to the top, the temperature should be about 8 degrees cooler at the top, 8 degrees Celsius cooler than it is at the surface. So if you like cool weather, the top of the Burj Khalifa might be a nice place to buy a house, if you can afford it, which I can't. I couldn't afford a broom closet in the Burj Khalifa, much less a house. All right. So adiabatic lapse rate, this dashed line, that's like the typical, on average, how much the temperature of air is decreasing as you go up in the atmosphere. So if the air temperature, sometimes the air temperature, just because of the weather or maybe because of environmental factors, sometimes the temperature changes a lot more quickly than 1 degree Celsius for every 100 meters. So super adiabatic, what that means is that if you go up to the top of the Burj Khalifa and it's 20 degrees colder than it is down below, that would be an example of super adiabatic conditions, when it's cooling more quickly than expected. Subadiabatic means that it's cooling less quickly than expected. As you go up through the atmosphere, adiabatic conditions means that there isn't much of a change in temperature as we go up through the atmosphere. And there's even something called an inversion, which is kind of unusual, but occasionally it actually gets warmer as you go up through the atmosphere. We'll talk about what causes an inversion and what the environmental consequences of that can be. Again, to emphasize, superadiabatic means the temperature is changing more than the lapse rate. Subadiabatic means the temperature change is less than the lapse rate. And the lapse rate is the typical, what it should be changing, just based on how much gases expand as a function of temperature. Okay, so on the top, this first figure is showing if we had subadiabatic conditions, then what we're going to have is unstable. Unstable means that a certain packet of air, if it rises, then think about if it started at 20 degrees Celsius and it goes up 500 meters, then it should decrease by 5 degrees Celsius. But if the prevailing temperatures, prevailing means the temperature of the air that's surrounding it, if the prevailing temperature is 10 degrees Celsius, then it's going to continue to rise. Whereas a subadiabatic condition is considered stable because a packet of air that rises and goes up 500 meters, just this packet of air is going to cool by 5 degrees Celsius, but the surrounding air is 18, which means the surrounding air is warmer, and so the cold air will go back down again. So the thing to pay attention to in this figure is the difference between prevailing, which means the actual atmospheric conditions, and then this packet of air is maybe some air that's coming out of a smokestack. Air that's coming out of a smokestack is going to be warmer or cooler than the surrounding air, and it's being injected into the atmosphere at a certain height. If you had a smokestack and the height of that stack is 500 meters, then it's going to be putting air into the surrounding gases that's at a different temperature than those surrounding gases. And so the surrounding gases are the prevailing conditions, and then the packet of air that we're delivering into the surrounding air may rise or fall depending on the temperature and depending on if the atmospheric conditions on a certain day are superadiabatic or subadiabatic. These are some of the smoke plume patterns that can arise depending on those conditions. For example, if you have superadiabatic conditions, meaning that the temperature is changing a lot with elevation, that can cause a looping plume, where the smoke goes up and then down and then up and then down again. It's looping because the surrounding temperature doesn't support a steady dispersal of the pollutant. Here you can see what's called a coning plume, and that's typical for stable conditions, for subadiabatic conditions. And here's that inversion, which is the strange condition that the air is actually warming up as you go upwards. Inversions can cause a lot of funny behavior with pollution. It can cause the pollution so that it can't go any lower than a certain level if the smokestack is above the inversion. So that's actually a good thing. That's good for us because we live at the surface, and so it's great if our smokestack is higher than the inversion layer. But what's really bad is this. If your smokestack is lower than the inversion layer, it traps the pollution. And so the pollution can't go any higher into the atmosphere. And so if you're living down below an inversion, and there's a lot of emissions like from vehicles or people's cooking fires or industry, the conditions can be very bad. And in fact, they can be deadly below an inversion. Here's a little bit more information about what causes an inversion. They happen a lot with mountain valleys. Like, for example, Tehran is surrounded on all sides by mountains. And it's kind of known for having, in the wintertime, difficult pollution conditions. Because what happens is when warm air comes in very quickly, after an extended period of cold conditions, the ground is cold and suddenly warm air comes above it. Well, then you've got the warm air trapping the cold down below. Because remember, warm air rises, cold air sinks. And so all this cold air is stuck because it can't rise. It's going to take a long time for the soil to warm up. During the winter time, when you've had extended cold conditions, then the soil is frozen, the buildings are cold, and so it takes really a long time for the surface to warm again. So in the meanwhile, for days and sometimes weeks at a time, you can have warm air above the cold air, and then whatever pollution there is that's being generated inside the layer of cold air gets stuck. There isn't going to be very much mixing between the warm layer and the cold layer. And this is sort of like temperature stratification in a lake. Remember when we talked about how a lake becomes stratified and there can be anaerobic conditions down below and aerobic conditions up above? The same thing is true in atmospheric considerations, where if we have pollution being emitted inside the inversion layer, then it can be really deadly for the people who live in that. Here's a picture of the town I was born in. This is Salt Lake City, Utah. It's surrounded on all sides by mountains. And so if you were down below inside the city, it would seem like foggy day. And it would be foggy actually not just day, but foggy for weeks sometimes. 3 weeks, I think even 4 weeks. One time they had an inversion that lasted an entire month. But if you climb up into the mountains or go to the ski resorts in the foothills, then it's clear and sunny, and actually it's warmer up on the mountains than it is down below in the valley. So, by the way, all this white stuff, that's snow. Yeah. All right. Let's take a look at an inversion that happened in London. Back in 1952, in London, they had the problem of an inversion that lasted for several weeks, and during that time, coal was being burned. Coal at that time had much higher sulfur content than it does now. The typical sulfur content back in the 50s was about 4%. So coal is mostly carbon, but then there are some impurities as well. One of the impurities is sulfur. And the problem with that is that when you burn sulfur, it combines to form SO2, sulfur dioxide, which forms acid rain, but it's also really bad for your lungs. For the same reason that it's bad for trees and cars, it irritates the lungs. So what we know is that the area of the greater London area is about 12,000 square kilometers. And within that area, there was 25,000 metric tons of coal that were burned. Does anyone know how many kilograms there is in a metric ton? 1,000. Right. So 1 metric ton equals 1,000 kilograms. So we know the average mixing depth, that means the height of the inversion, was about 150 meters. So what we can calculate is the volume of air and also the mass of sulfur that was burned. And then since we know the relationship between the mass of sulfur and the mass of SO2, we can find out how much sulfur dioxide entered the area. Everybody have a copy of today's in-class exercise paper? All right. Go through parts A through D, and step by step, we're going to see if we can figure out what is the concentration in micrograms per cubic meter, and then we're going to look at the limit and see how this inversion compared to the emission limits that would be in place today. Let's take a look at the solution for this one. Okay, the first thing we need to do for the volume is convert kilometers into square meters. 1 kilometer is 1,000 meters by 1,000 meters. So then you can get the area in meters. And we multiply that by the height. Our mixing depth is 150 meters. So the total volume of air that all this pollution is going to go into is 1.8 times 10 to the 11th cubic meters. Remember, in the end, we're trying to find a concentration. The definition of concentration is mass per volume. So here's the denominator of that factor. It's the volume. Now we're going to talk about mass. The mass of sulfur, since the coal back then was about 4% sulfur, that means 4% of the 25,000 metric tons is sulfur that was burned. So 4%, and then I converted the tons into kilograms. So 1 times 10 to the 6th kilograms of sulfur. That's the molar ratio of sulfur to sulfur dioxide. The molar ratio is 1 to 1. But the mass ratio is 64.062 to 32.064. So from the ratio of the molecular weights, you can find out what mass of SO2 is emitted. They burn the sulfur and it turns into sulfur dioxide. It's a combustion reaction. And it's going into this volume of air that's stuck above London. And there can't be any mixing because it's inversion conditions. So during this inversion, which lasted for several weeks, almost 2 to the 6th kilograms of sulfur dioxide was emitted into the air. So concentration is just going to be the mass divided by the volume. And we find out that it's 11,000 micrograms per cubic meter. I don't know, is that a lot? It kind of sounds like a lot. The only way to know if that's a lot is to either look at what happened or look at like what the air quality standards are nowadays. So the first part of that, what happened from this event? On the earlier slide, there was 12,000 people who died during this period. A really huge spike in the death rate, and it was related to the air pollution. And we see the same thing even today, not in the same numbers, but usually it is older people or people who already have chronic lung conditions. Sometimes it's children with asthma that are affected during these kinds of inversion events. And there's a direct relationship between inversion and hospital admissions for respiratory illness. Mm-hmm.
Doesn't that number also include the side effects like from traffic accidents? Because people
I'm not sure how that was calculated. It could be traffic accidents as well because yeah, it does look like it would be pretty hard to get around. This is during the day that people had on their lights. So 11,000 micrograms per cubic meter. What's the limit today? Here's the U.S. limit. The U.S. limit says that during a 24-hour period, during one day, the average should be 365 or lower. This is the U.S. standard. Here is a proposed rule that was being considered in Abu Dhabi several years ago, and they said that during a 24-hour period, the maximum limit should be 125. They look at the sensitivity of people to a certain chemical, and they look at, you also notice that the time is different. For a 1-hour period, they're saying it's okay to have 1 hour of 350. For 24 hours, for a longer time, the concentration should be lower. So if you're only going to be exposed for a short period of time, then it's okay for the concentration to be bigger. And sometimes they also make a compromise depending on how hard it is to achieve the regulation. In Abu Dhabi, it's probably easier to achieve good air quality than it is in Tehran because Tehran is surrounded by mountains and Abu Dhabi has the sea. So the sea breeze coming in helps to cause a lot of mixing and carry the pollution out of the city center.
So don't they also take into account the size of the city?
I'm not sure if they do or not.
Since the concentration is not on the volume, but you have bigger volume.
Yeah. Well, the size of the city certainly is going to influence how much pollution there is, but I don't know if they'll change what the legal limit is based on the size of the city. All right. So here are some of the things that are regulated besides SO2. That's not the only air pollutant out there. Sometimes carbon monoxide is a real problem. Carbon monoxide is formed from the incomplete combustion of hydrocarbons. And sometimes you maybe hear about someone has a fire burning inside their house and in the morning everyone is dead, right? It's carbon monoxide that causes that sort of thing, where the water heater malfunctioned or maybe cooking gas wasn't burning all the way. And carbon monoxide is really dangerous in terms of indoor air quality. There are also rules on the outdoor air concentrations of carbon monoxide. Lead isn't as much of an air quality concern as it used to be. Do you know why back in the older times lead was more of an air quality issue than it is now? That's right. It used to be added as an anti-knock agent to fuel. So nowadays we use unleaded fuel, but back until the early 80s it was added just to make engines run more smooth, lead. Luckily we don't do that anymore. NO2, nitrogen dioxide, it causes acid rain in the same way that SO2 does. It forms nitric acid instead of sulfuric acid. Ozone is interesting because usually we think about ozone as being a good thing. Have you heard about the ozone layer? The ozone layer is really important. It's high in the atmosphere, and what does the ozone layer do? Right, it shields the Earth from getting too much UV. Down in places where they're exposed to the hole in the ozone layer, like in the southern hemisphere, South Argentina, Chile, Australia, there are places in the far south where they have to be a lot more careful about getting sunburn than they used to, because the type of gases that were used as refrigerants, chlorofluorocarbons, would go into the atmosphere and attack ozone. So the ozone really high in the atmosphere is good because it protects us from too much UV. Ozone at the ground level, at the street, ozone is bad. It irritates your eyes, it irritates your lungs, and so ozone is another gas that's given off by vehicle pollution. So we like it really high in the atmosphere, but we don't like it low in the atmosphere. Naturally occurring ozone is good, artificial ozone is bad. One last thing. PM10 and PM2.5. The PM stands for particulate matter. And have you ever driven behind a bus and seen a huge cloud of black smoke? That's particulate matter. That really thick black smoke that you see. Diesel is wonderful in terms of fuel efficiency, but it's really terrible in terms of particulate matter. It's very difficult because of the composition of diesel fuel and the really high compression ratios that are used. It forms these tiny, tiny little particles, and the 10 and the 2.5 is talking about the diameter of the particle, so the size of it. 10 would be 10 microns in diameter, and 2.5 is even more dangerous than 10 because the smaller the diameter of the particle, the deeper into your lungs that particle can get. It can travel into the very, very small recesses of your lung, and once the particle gets in, it's almost impossible for it to get out again, no matter how hard you cough, and so it gets in there and just persistently irritates the lining of the lungs. So here are some pollutants that are regulated. There are others as well that are dangerous, but these are the main ones that we have to sort of analyze and keep in mind when it comes to the air quality in cities. Mm-hmm. They're dangerous in their own special way. You know, like, yeah, if I had to choose between being in a room with carbon monoxide and sulfur dioxide, one way to look at it is what's the limit? It seems like the limit is lower for SO2, so that would imply it's more dangerous than carbon monoxide. But then on the other hand, one of them is going to irritate your eyes and lungs, and the other one's going to kill you. So, pardon me? Yeah. I suppose it's just because it takes a higher concentration in order to kill you. You know, they set these limits in terms of how much causes an effect on people. And so there has to be a lot. It's a devastating effect, but apparently it looks like you can stand 1 hour of exposure, you can have 40,000 micrograms per cubic meter for one hour. I don't know how you'd feel after an hour of that. You'd probably get a headache. That's one of the things they say, is that sometimes when people are in that enclosed space and they're exposed to carbon monoxide, they have just really a terrible headache. They're disoriented. That's one of the warning effects that people get before they're completely overcome. The reason it kills you is it actually takes the oxygen out of your blood. Carbon monoxide will take it out of the hemoglobin. We talked about inversions, and inversions are bad because it means there's not enough mixing and it keeps the pollution close to people. Sometimes cities can have inversion during the day just because the Earth's surface gets warm during the day, and then when it starts to cool off up above, then all of the heat that was, think about how hot the pavement and asphalt gets from the hours of the day when it's getting the sun onto it. The air up above is cool, the ground down beneath is warm. That's the definition of an inversion. And so here in the UAE, one of the inversion types that we can be a victim of isn't necessarily the kind of inversion where you're surrounded by mountains, because we don't have mountains all around us here. But we could have a radiation inversion. Radiation not in the sense of like nuclear radiation. They're just talking about radiation from the sun, thermal radiation. And so in the evening, there's the case where, see, at midnight, the curve is that the temperature is increasing with elevation. And that's the definition of inversion, is that it's warmer up above. And when it's warm up above and cool down beneath, then the pollution doesn't, it's trapped. It can't diffuse. All right, it's 12:50. We're out of time. Let's just take one look at the announcements before we leave for the weekend. Remember, your focus should be on getting the draft version of Part 2 together. You can do some research over the weekend and start writing up your findings. And if you have any questions about your exam, I'm more than happy to go over it with you. I've got the solution, and so feel free to come to my office during my office hours, or we can make an appointment if that doesn't work. See you later.